Hello, today we're going to talk about rotational motion. So here you might recall we had the equations for linear motion with constant acceleration A. So you can find these in any physics textbook. The symbols may be a little different, but here I'm using x as a linear displacement, v is a linear velocity. That means, say, in the x direction, the velocity in the x direction in this case. A is the acceleration, and this is a final velocity, an initial velocity, and so forth. So you may have to review a little bit your linear motion. But you might notice that these equations, which are used for rotational motion, are very similar. So I'll derive these equations from these later on. But these equations describe a rotating object such as a bicycle wheel that's rotating at an angular velocity omega. So this would be, in common usage, revolutions per minute, but those may not be the most desirable unit, so you have to learn to convert from revolutions per minute or whatever to SI units usually. So here, just in case you are not all that familiar with Greek, this is the Greek letter alpha, this is the Greek letter theta, and this is the Greek letter omega. So omega is used for an angular velocity, like I mentioned, revolutions per minute. Theta is for an angular displacement, that a rotating object would rotate through an angle theta. And then alpha is used for an angular acceleration. It could be the case that, say, you're pedaling your bicycle faster and faster and faster, the tires are going to rotate faster and faster and faster. That's an angular acceleration. So anyway, if this is a bicycle tire, this could be a spoke, and all the spokes have the same angular velocity and the same angular acceleration. But the tangential velocity, say you had a rock stuck in your tire and it flew out, it would fly out with a certain tangential velocity. That depends on the radius. A bigger tire rotating at the same speed as a smaller tire would throw a rock out at a greater tangential velocity because it's got a greater radius, and I'll show you that in a minute. So first I just want to review what a radian is. That you may recall this formula from trigonometry, that an angle in radians is given by the arc length that subtends this angle theta divided by the radius. So you can see that from this figure that I've got drawn up here, that S is the distance along the circle and R is its radius. So if you want to calculate this angle in radians, then you divide the arc length by the radius. So 1 radian is defined. They use 3 equals here instead of 2 bars for equals. That's supposed to be a line. That 1 radian would be the angle formed when the arc length S is equal to the radius. So if you had a complete circle, the angle formed would be, your arc length would be the circumference of the circle divided by the radius. So that's 2 pi radians. And then you might recall that there's 360 degrees in a circle. The angle formed by a complete circle is 360 degrees. That equals 2 pi radians. So then you get a conversion factor between degrees and radians. Divide this by 2, so you get 180 degrees equals 2 pi, just pi radians. Let me scratch that out. That should be pi radians. So let me give you some examples of converting degrees to radians and radians to degrees. I'll do that in the next page. Let me clear this page. So for example, say you had 45 degrees and you want to convert that to radians. There's pi radians per 180 degrees. So that equals pi over 4. So you just cancel out the degrees and do the arithmetic here. So you could leave that like that, and in math they would leave it as pi over 4, but you could divide this out, and this is approximately equal to 0.785 radian. Okay, just one more like that. Say you had 30 degrees. So you multiply that by 180. So you want to get rid of degrees, so you put the 180 degrees in the denominator and the pi in the numerator. So that turns out to be pi over 6. And then you could do the arithmetic here, divide pi by 6. Okay, just one more. Say you had pi over 6 radians. Or let's change it to pi over 3 radians. And then, so you want to end up with degrees, so you put the degrees on the top and put the pi on the bottom, or in the denominator. So here you get 60 degrees, right? So pi over 3 radians is 60 degrees. Okay, just one more. Say you had 1.5 revolutions as an angle. Sometimes they give you an angle in revolutions. So you might recall that there's 360 degrees per revolution. So that would be equivalent to 540 degrees. And then they may want that in radians, so then you would have to multiply that by, there's 2 pi radians per 360 degrees, or you could use the pi over 180, which would be a little easier. So anyway, that would be 3 pi radians. 180 into 540 is 3. So this is a good conversion factor to know too, that either 2 pi radians is a revolution or 360 degrees is a revolution. Okay, let me come up here and develop some more formulas. Say you got something rotating about an axis, and that's the angular velocity, omega. So in a time delta t, it rotates through a distance delta s on here. I'll draw that. This is delta s, and it goes through an angle delta theta in that same time. So this is basically the formula S equals R theta. But this is rotating, so they say it goes through an angle delta theta in a time delta t. And during that same time, a point on the circle would have traveled the distance delta s. So a change in distance over a change in time is a velocity. And they called this is the definition of omega, the change in angle per time. So I put a t on this velocity because what that gives you is, I'll draw it up here just for clarity, that say this were a rock stuck in a tread and it worked its way loose and flew out off the rotating tire. It would have, as soon as it left the tire, would have this speed they call v tangential. It's tangent to the circle, meaning it's perpendicular to a radius right there. So that's a tangential velocity. And then you could carry this one step further, that if this tire is speeding up and up and up, it's going to have a change in velocity over a change in time. This is the v tangential. So this is the tangential acceleration. And then they define the change in angular velocity per time as angular acceleration. So I'll have to continue this in the next video.